Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by i.i.d, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good afternoon, ladies and gentlemen. It's a great pleasure to welcome you to the next webinar series of the AI for Earth and Sustainability Science webinar. My name is Joachim Denzler. I'm co-leading the LS unit in Jena and heading the computer vision group at the University of Jena. And it's my pleasure to welcome our today's speakers, Jonas Peters, here in this session. Jonas is an excellent, I think, one of the distinguished scientists in causality research. He's studied mathematics at the University of Heidelberg and the University of Cambridge and obtained a PhD jointly from the Max Planck Institute and ETH. After that, he was professor at the Department of Mathematical Sciences at the University of Copenhagen and a group leader at the Max Planck Institute for Intelligent Systems in Tübingen. And since 23 now, he is professor of statistics at ETH Zurich and is well known for all his different contributions to causality research, which is especially important if we look at a highly dynamic and complex system like our Earth system. And I'm looking forward to the next 40 minutes and your presentation, Jonas. Jonas, please go ahead.
Yeah, thank you very much, Joachim. It's a great pleasure to be here. It's an initiative that I really like, so I'm happy to be able to speak. So I hope the sound works okay. Otherwise, just please mention this. Or if there's something wrong with the connection, just jump in. Let me see if I can share the screen now. Do like this. And then I go to full screen. So I hope that you can see my slide now. If not, then just let me know.
We can. Hi, Jonas. Just quickly jump in. We can see it, but not in full screen. I'm not sure.
I think that's okay. I don't know where this is coming from. Should be fine. Thank you. So I'm going to talk about causality in dynamical systems. And this is, if you like, the too long, do not listen version of this talk. So we are really working in between methodology and applications. And we are at least aiming to always use these applied problems as our motivation for the direction in which we would like to change our methodology. Our focus is, as you have heard, often on causality, but sometimes, in particular in the recent years, we are also looking at robust prediction methods and also more complex data structures. And sort of the most important point here is if you have any problems that you would like us to study and see whether we can help, then please reach out. I should say, though, ideally wait for a couple of days because my family is sick and including me. So I hope my voice doesn't break down until the end of the talk. But we are always very happy to receive sort of problems and questions in between. Okay, let me just see whether if I do this once more. Oh, this didn't work. I'll just do it full screen like this. I think that should be better. Okay. Where's this coming from? Just give me 1 second. Sorry. Okay. This could work. So this is a very small sort of 1 minute takeaway of how you can view causal systems and causal models. This is something that at least I find instructive to think about. So this is a hierarchy, if you like, of 3 different types of models. At the top, you have sort of the most valuable one. These are mechanistic models, physical models. So think about a global climate model, for example, where you really understand a lot of the system. And what you can do with this, of course, you can now predict in an i.i.d. setting, but importantly, you can also predict under interventions. So you can ask now, well, what happens if, for example, I change the CO2 concentration in the atmosphere to an arbitrary amount, and you can run these mechanistic models to see what happens. The third column, this is this falsification. So if someone claims, well, this is the physical model of the system, how could I falsify the statement? Well, there are two versions, right? I can just check whether the observational distribution that comes out of this model is matching the data that I see. So we have tests for this. But you can also sometimes actually run the interventional experiment and then see whether the predictions under this intervention match the data that I see in this interventional experiment. Now, in the bottom, this is sort of the weakest model, if you like, a statistical model. It's the weakest of these three, but of course, it's very powerful. Nowadays, we see a lot of amazing applications of AI and machine learning in all sorts of different domains. But it's weakest in this hierarchy in the sense that you can use it to predict in an i.i.d. setting, but you cannot use it for prediction under interventions. There are many ways of seeing this. So one is just to say that there are different causal models or different physical models that give rise to the same observational distribution, but that provide different answers under interventions. So this just means if you only have a statistical model, you don't know what happens under interventions because it could correspond to actually several different physical models. Now, what is this stuff in between? This is what we are trying to study. These are causal models, and these are really in between in the sense that they are mathematical models that help us to predict under intervention, but they don't give us this physical insight. So can this still be useful? I would argue yes, at least in many scenarios, not in all, but in many. And I was told, I mean, I guess some of you know this much better than I, but I was told by my medical doctor friends that some of the anesthesia that we are using currently for very good reason, and I'm happy that they exist, there we have a good understanding of a causal model. So we know how much to give to which patient and what effect to expect. But we don't actually understand the underlying physical processes. And still, I would say it's a very useful model to have. Now, this is a bit of a bold statement, but I would claim that confounding, and in particular hidden confounding, this is one of the key problems in causal inference. So this, what is causal inference? Think about, we are somehow trying to find a causal model from data. And this confounding, I'm going to explain this in a simple example in a second. This is really one of the big obstacles we have to tackle. And then in a couple of minutes, I will try to argue that actually in these dynamical systems, there are a couple of ways of dealing with such confounding. But let's first remind ourselves what I mean by this. This is a data set. This is very old now, but it's one that I'm using sometimes in lectures as well, because it has a nice illustrative purpose. So this is about whether children develop myopia, so this is short-sightedness, after 2 years. So what are the conditions that they study here? They study the nightlight conditions of the children before they measure the eyesight. So some people or some of these children sleep in completely dark rooms. This is shown on the left. Some sleep with a nightlight. These are these things that you put into the plug, and then this gives a bit of light. And then some sleep in bright room light conditions. And what you see here is in yellow, the fraction of myopia as percentage of subjects. And you see here it rises the more light you see during the night. So now I provide some more numbers here. You don't have to recalculate them. This is just the overall prevalence of these conditions. Myopia, for example, is present in total 26% of the children. This is just a weighted average, if you like, of these 3 yellow numbers here. And now an interventional question is of the following types. So what happens if we make all babies sleep with room light? How many will develop myopia? So I provide you with 4 different answers. The first one is 48%. The second one is 26%. The third one is 8%. number that doesn't have to seem to have to do with anything at all here? Or is the answer D, I cannot read the above answers? So you can think about this for a couple of seconds and think about what the correct answer to this question could be. And as you may guess, of course, the answer is it depends. Why? Because let's say we are in a world where there's no confounding. So the night light conditions has a direct causal influence on the eyesight conditions of the child. Then the answer would be 48%, because if you just make the baby sleep under room light condition, then we would see myopia in 48% of the children. However, the real world looks quite different. Let's call this world 2. Namely, one has found out that there's what we call a confounder, namely a variable that influences both the lighting conditions in the room and the eyesight conditions of the children. And this is the eyesight of the parent. Maybe not surprising to some of you. So if the parents suffer from myopia, then more often they would put bright lights into the children's rooms. And also the eyesight conditions of the children seem to be on average worse in terms of myopia. So here, this is what we call a confounder. It influences both of our variables of interest. You can say, well, this we could measure, right? So then we would say this is an observed confounder, and there's a lot of very good literature on how to deal with these confounders if we can measure them. So this is well studied. There are like an enormous amount of techniques, very involved techniques, very simple techniques, some that are interpretable very easily, some that are more involved, have better statistical properties. So dealing with observed confounders, this is sort of the bread and the butter, if you like, from a person working in causal inference. The problem, however, is that in many of the examples that we look at in real world, there could be another variable that we maybe don't measure. Maybe we have an idea what it could be, but we cannot measure it. Maybe we cannot even think about what it could be, but there could always be a hidden variable influencing both. And then this makes our statistical inference much harder. Why is the 26% here the correct answer? Of course, because if the scenario is like this, then the answer is particularly simple, because if we intervene now on the lighting conditions, well, what happens to the eyesight conditions? Nothing, in the sense that it just remains what it was before, if there's no direct causal link. So what was it before? In the overall population, we saw it in 26% of the children. Okay, this is just an hopefully illustrative example of what we mean by confounding. And now the question is, well, what does this have to do with dynamical models? And the first showcase of dynamical models I want to talk about, this is the claim that they can remove hidden confounding. This is joint work with Felix Schur, who's a PhD student here. Okay, let me give you an example. So now we are again looking at two random variables, x and y, but now we observe them over time. And here you see just two time series, if you like. And now the goal, what we try to find out is, what is the causal effect from x to y? You can see that they are correlated roughly, right? Because it seems to be that in time points where x is relatively large, then maybe also y is on average a bit larger than it usually is. So there's a correlation. The question is it also causal? Okay, so what we can do is we can, of course, just plot y against x. And even if we think, my apologies, even if we think that the effect might be instantaneous, there's the following problem. So if you just regress y on x, let's say linearly for now, we might find this regression curve that is the orange, but due to confounding, it could be, this is the case here, that the ground truth causal effect is actually different. It's, in this case, it's smaller in absolute value. It's the slope of this orange dashed line. So this is the ground truth, which we know because it's simulated data. But how on earth could we figure this out from just looking at the data? And in this work, we are studying a very simple idea, and I'm presenting this here. So we are trying to apply this to a couple of relevant scenarios, as I'm going to explain later. But we very much hope that maybe this idea is something that resonates with you, and maybe you can think about other applications or similar problems, and maybe even problems where we need to extend this idea to, then please reach out. Okay, so what is the underlying idea? We assume that there's a hidden confounder. Okay, fair enough. This is also a time series. And now the simple assumption that we want to make use of is to say that it's sparse and frequency domain. So let me write this down. So we call this method decore, so deconfounding in time series with robust regression. We assume that the confounder, even though we don't observe it, we assume that there might be a confounder, but it's sparse and frequency domain. How can we sort of, now even in this assumption, how can we exploit this? It's certainly not true always, but let's say it is. So let's say you assume the seasonal cycle as a confounder, then it would be true, but we would even know the confounder. How could we make use of this assumption? Well, the idea is now to Fourier transform the data and think about any Fourier transform that you like. It actually works with all bases. I just call this basis here phi. We often use the cosine basis, but just think about the Fourier transform. And then we perform robust regression. Why is this? Because the effect of the confounder, this will be sparse in the frequency domain. So what we are going to see is that if we have a linear relationship, for example, from x to y, we transform the data. So we look at the Fourier transform of x and y. Then the effect of the confounder, because it's sparse, this will only correspond to a couple of data points in the new basis. So let's look at this in action. So this is the same plot from before. On the left-hand side, you see the data in the time domain. So this is where the regression does not work. So the OLS gives us a biased estimate. So this is not equal to the dashed line. But now we do the very simple trick. We just transform the data into the frequency domain. And then the picture that we see is as follows. So we have these data points that you see on the right. But now each data point corresponds, if you like, to a frequency. And now, because the confounder is assumed to be sparse in the frequency domain, it only affects some of these frequencies. So this means that for many of the frequencies, the regression, if you were to draw a regression line, would give almost a perfect answer. But some of the data points, they are sort of stemming from this confounding, they are off. So they are not showing sort of the right behavior. So this means that, well, if you just regress now in the Fourier domain, so in this frequency domain, we would still get a wrong answer. This is what you get. This is again, the orange line. So this is still incorrect because it now pools the sort of the good cases. These are the gray data points, and the confounded cases, the purple. Here, for illustration purposes, we have colored them because it's a simulated data set. So we know which frequencies correspond to the confounder and which one to the unconfounded data set. But of course, in reality, we don't. So what can we do? Well, this is not an impossible task to solve, right? Because you can think of this now as a robust regression problem, where you're saying the bulk of the data is actually showing what I'm trying to estimate, but some of the data points, they are off. So think about them being outliers. And now, in principle, you can run any, we call this robust regression technique that you like. So you can also run outlier detection, for example. What we are doing is something that is called torrent, but this is a choice. You can do many other things as well. It's just that for this algorithm, you get a lot of guarantees that we can then exploit also to understand the problem a bit more theoretically. But in principle, the idea now is to say you transform the data to the frequency domain, and then you're just trying to find out which of the data points are gray and which are purple, because in reality, they're not labeled like this. And you're doing this by saying, okay, I'm running a robust regression technique. A very simple method, we call this sometimes brute force search. It's just something that you cannot do in practice, but conceptually you can think about this. You're saying, okay, if I know, let's say that 5% of my data points are confounded, so this corresponds, right, to the sparsity assumption of our confounder, then you're just saying, okay, I'm trying to find a subset of, let's say, 95% of the data, and I'm trying to find the subset such that if I regress and look at the residual sum of squares will be as small as possible. So this is conceptually the right thing to do. Of course, practically not, because we cannot go through all subsets that contain 95% of the data points. So I very much hope that this figure shows the main idea. I'm going to put a bit more math on this now, but this is really only for sort of trying to explain the same idea just in different words. So hopefully this figure makes sense, and if not, then please ask again, because probably then I didn't explain it well enough. Okay, so what is the model? So here I'm going to come back to this in a minute, but let's for now assume that the model is linear. So y is just a linear function of x and y are observed, right? And we have this confounder u, and then we have some additional noise eta. They are all now stochastic processes, and we are trying to find out the beta. So what is the causal effect from x to y? And then we have almost no assumptions on the stochastic processes themselves. Importantly now, the noise is now independent of x, right? So the confounding is really about this u now. So this is our confounder, and this we need to control. What is the data? We are now observing time series. So think about, so here the different ways of writing this down. We think about having sort of a time horizon between 0 and t, and now we're just observing more and more data in it. You can also think about that the upper bound of this interval is growing, is sort of mathematically slightly different, but it's conceptually the same. And then we have, of course, the observed data for y as well. Okay, what is our consumption? This is now saying the confounder, this u, is sparse in the frequency domain. How do we write this? Well, this is a very mathematical way of writing it, but we are saying if you transform the confounder into the Fourier domain, then the corresponding contribution, if you like, is 0 for almost all cases, except for this, what we call capital B. These are this B for bad, if you like. These are the bad frequencies. So these were the outliers in the right regression plot that you saw. So these are the ones we are saying there cannot be too many, and sort of outside these bad frequencies, the confounder doesn't play any role. Okay, and then this is just writing down the math. Again, if this feels a bit weird, then just ignore it. It's not important for understanding the idea. Just if you're interested, this shows how trivial it is, we think, but hopefully this makes it also powerful. Let's see. So this is just the Fourier transform. So we fix a basis phi, think about a cosine basis. And then, of course, we have different frequencies. And because we have data, we have as many frequencies as data points, and then this k is the running parameter. And because this Fourier transform is linear, we also have the same linear relationship also holds in the frequency domain. It's just now saying that, well, this Fourier transform of the confounder, this is contributing nothing to the regression in the frequency domain unless we are in these bad frequencies. And if capital B is small, then you can try to find this out. This is a problem that has been studied in statistics as well. So we call this often called robust regression, right? So try to do a regression, but you know some of the data points are off. And you can use something like brute force search, but this is just a much faster algorithm here, but there are many other techniques as well. Right, so maybe one quick word about what is Torrent doing. Just think about running bit of a greedy algorithm is something that should be very fast, right? So you're just starting, let's say, with the overall regression. You get the orange line. And now what you're just saying is you're looking at the residual sum of squares or the residuals that are the largest. So what could this be here? So some of these purple dots have a very large residual. If you look at the orange line, these you throw out. Then you're saying, okay, this is my current best guess of the gray dots. You run the regression again. You again look at the largest residuals. You throw them out, and this converges in practice quite quickly. So this is just it's one way, as I said, but you just have to make sure that you're not running through all the subsets, because this will take forever, of course. Okay, just very quickly, I promise some takeaways from the theory there, because they are, I hope, they're relatively intuitive. So one is, every guarantee you get for the robust regression yields guarantees for this overall algorithm, because this is really what you need to do. You need to be able to identify these bad frequencies, if you like. And then some of the assumptions, this is more relevant now for applications. So X itself, this must be somehow non-sparse in frequency domain. Why is this? Because of course we want X to be active almost like on a big band of frequencies, because then we can identify sort of which data points are affected by the confounder, and these should be few, right? So if X is active only on in 10 frequencies, and then we have a confounder of 8 frequencies, which one could say it's sparse, but then X is so sparse in frequency domain as well, then you cannot do anything. So this comes out of theory, and it's hopefully also intuitive. The other one, this is very mathematical, but so if you say that Cn, this is the upper bound on confounded frequencies, the question is a bit like, how sparse does the confounder have to be? And the answer is sort of, it doesn't have to be that sparse. So clearly, it must be, so if you think again about this robust regression plot, we cannot, if you have more than half of the data points being corrupted, then we cannot find out what the underlying ground truth anymore so we need to have sparsity, so it must be at least active in only, at most active in only n half of the frequency. That makes sense. And then so we get expressions of this type. So this just means, okay, when does it converge? And here we see that as long as the fraction of confounded frequencies, these are the bad cases, goes to 0, you divide by n, then we get consistency. And if you have band limited processes, so saying that your process that you start with is only active in a certain frequency band, then you even get stronger results. Okay, so this was this first case. We applied this to a study that we knew existed. So this is the second part of the showcase. Can we disentangle external forcing from internal variability? This is a study, if you like, that we just redid because you can apply our method too. What is this idea? So this is really taken from a paper from Sebastian Sippel et al., where the scientists try to disentangle, you take a target variable like precipitation, and they try to disentangle how much of the variability is actually due to internal variability of the system and how much is due to external forcing. So this is, I'm pretty sure that many of you know much more about these systems than we do, but I hope it becomes clear that it resembles the same structure, right? Because this is a causal effect that you are interested in from X to Y. And then you have this confounder, and maybe you can put this into a variable, but external forcing. So you can also say, maybe I consider this as hidden now if I don't have a variable available that sort of corresponds to all the external forcing that I'm interested in. And what the scientists did is they said, okay, if the external forcing is smooth, so this means that, let's say it's only active in low frequency domains, you can actually try to estimate this effect of interest from X to Y by looking at the high frequencies. And we are just saying, oh, that's true. And you can even do this if you don't know where the external forcing is active. Because we can just run this idea now, just transform X and Y both in the frequency domain. We are ending up with probably something like a robust regression technique. And then we just try to figure out ourselves which of the frequencies don't really match sort of the overall pattern. And if you do this, you get results that I'm explaining in a minute that are not so far away from the ones presented by Sippel et al. On the left, however, this is maybe interesting to see also, is the frequencies that, if you're running the robust regressions, that are kicked out. So these are the ones, these are the outliers detected by the method, right? These are the frequencies where we think, okay, they don't seem to match the overall pattern of the data. And you see that indeed it's the low frequencies that get kicked out a bit more than the high frequencies. How do we evaluate this result? This is, of course, tricky. It's a bit more probably a question to you than for us, I feel. But so what you can do is you can then say, well, okay, if this is really true, we can try to predict the mean precipitation into the future, taking out the external forcing. And this is what's shown on the right. So this is centered average 5-year precipitation in the Alps over time. And if you like, the ground truth data here is the precipitation provided by this Climax project. And if you like, there's at least, this is how far we understand it, it's at least reasonable to assume a pattern like this, because with the external forcing, you would expect that the ground truth is indeed showing this upwards trend. And again, what did we do? We sort of applied the very same reasoning, just saying you can learn even, you can try to learn the frequencies that are confounded in this case, which would correspond to the external forcing. I should also mention that, so we actually, our work was at least partially motivated also by this work by Miguel Mahecha and others, who predict the temperature sensitivity of ecosystem respiration, where the basal respiration, the unobserved, in this case, the unobserved confounder, is slowly varying. So this is a similar idea, right? So there, I guess the seasonal cycle is very prominent. And again, you can say, well, there's certainly a confounding happening here, because there will be more respiration, I guess, if during summer, for example. And if we know in which frequencies the confounder is acting, we can try to remove these frequencies by hand. And we would again argue that's correct, of course. We can also try to learn this from data without putting this in as background knowledge. Okay, but again, so if this idea resonates, then please let us know. In particular, we are always interested also in realizing what obstacles there could be for methods to be applied in practical scenarios. I should also say that nonlinearities, there's nothing really linear. Parts of this idea is linear, but there's nothing that prevents us from applying this to nonlinear functions. And this is something that we are currently adding to the paper. This is a master student as well who's working on this. Okay, so this brings me to the sort of the second showcase, what you can do with dynamical systems. And it's similar in the following flavor. So somehow dynamical in the causal inference world, and this may now sound weird to you because a lot of real data is dynamic, of course, but in the causal inference world, we sometimes view this, we start sort of looking at systems where we don't have time and consider them a bit easier, and then saying, okay, if dynamics comes into play, we're trying to use similar techniques, similar methods, and just trying to incorporate the complex data structure. And I'm trying to make the point here that this is only half of the story, because if you're going to dynamical systems, there are also certain benefits that come. And for example, this idea of sparsity at the frequency domain that I just presented, this has no analog in the i.i.d. world. And similarly here, in the second showcase, we have now a case where we are using the dynamical models to deal with cyclic structures, something that I would argue would be much more difficult if you don't have time available. Okay, so what is a cyclic structure? Well, you can just draw it like this: A is influencing B, and B is influencing A. And in short, I'm arguing that I don't think this is a sensical, or this is. Let me put it this way: you can make this precise. It's a super complicated model to work with, and we are running very quickly in questions of, okay, what are we actually trying to model here? What I always recommend doing if you're working with causal models, think about an intervention that you can perform in reality, and phrase the question you're trying to solve in terms of interventions that we face in reality. So there are two common approaches of saying, okay, how can you model these cycles in a good way? And this is what I would say is a good way. So if we have time resolved over time, the system resolved over time, then we may have a cycle that is not instantaneous. So it could very well be that the past of B is influencing A and the past of A is influencing B. This is totally fine. And this would also correspond, if you like now, if you just collapse the system, then this would also correspond to these two edges. But this is much easier to study here, and there are much less problems coming with it. Similarly, if you have differential equation models, so this is studied this quite a lot from mass action kinetics point of view. So if you have differential equations, it could also be that the concentration of A is influencing the rate of change of B, and B is changing the concentration of B is changing the rate of change of A. And again, we have a cycle, but these systems are much easier to study. So my recommendation is, whenever you have a cycle, try to resolve it into something like this. One additional point, we will see in a minute, we are going to see these double-headed arrows. But these are not cycles, but these stand for hidden confounders. So for something that is unobserved, that is influencing both A and B at the same time. So this, with these double-headed arrows, I mean a confounder, something that we should study. And with these two edges, this is a cycle that we should avoid. Okay, so what is the problem we studied here? This problem from electricity market. So this is a question that was motivated by a group of our collaborators in Berlin who wanted to understand what happens to electricity demand if you increase the price. So this is usually called the price elasticity. And this joint work with Silvana, Roche, Oliver, Felix, and Leon. So trying to explain what the underlying question is, how does the electricity market work, at least in Germany? So in very simplified terms, it's like every company or person, if you like, running a power plant offers a bid. So says, okay, tomorrow at noon, I could produce, let's say, 1 gigawatt for this price. And then there's sort of all these bids are collected and they are sort of sorted according to price. And this is what you see here in this plot. This is called the merit order curve. And now next day, you're going to see, well, what is the actual electricity consumption? Let's say it's 40 gigawatt. Then what we're going to do is we're going to look at the last power plant that entered, and we looked at this bid. So here in this case, it would be something like 30 euros per megawatt hour, I guess. And then this is the price that we pay for all of the power plants. Now, this is the curve from 2018. This is from 2022. Of course, this terrible war in Ukraine started, which has many negative side effects. This is just one effect as well. So the price or the bids from these gas power plants, this changed a lot. And then, of course, also the corresponding price will change from time to time if we hit an electricity consumption that is beyond this steep increase here. Okay, now, obviously, the electricity consumption is not just given. It's not always 30 gigawatt, but it also follows some sort of principles, because some companies or some factories, they might say, well, if the price is like 200 or 400 euros per megawatt hour, I'm not going to produce anything because I will lose money. So there's something that is called the demand curve. And this more or less says the larger the price, the less the electricity consumption will be. And the underlying question is now, what is the slope of this curve? This is important for several reasons. In particular, you want to understand, well, how much, if you're interested in building safety of these electricity systems and you're projecting into the future, you need to see how the demand changes with an increase of price. And this is the target of our inference. So let's see how we deal with this. This is now one way of resolving the cycle. So where does the cycle come into play? We know that in these systems, we must have that demand equals supply. This is a physical system that's nice about electricity, is that if this constraint is violated, you will just see a change in frequency. So there's a physical reason that the demand must be equal to the supply. And some people would now draw sort of an edge from D to S and some from S to D. And we are trying to argue this is not the right way to do it. Instead, what we can do is we just try to find a third variable price that goes into the system. And then we are saying the demand depends on the price. And this coefficient is exactly the price elasticity, what we want to estimate. And the supply also depends on the price. Okay, fair enough. Now we just have the constraint that still exists, that supply must equal to demand. But this now yields a price at equilibrium. You can just, this trivial algebra, you can now solve this. And now this yields an equation for the price. What is nice about this is if we now draw the system just using demand and price, so if you forget supply for a second, then this is a system without cycles. But what we do have is we have a confounder, namely this randomness, this epsilon d here. This enters both the equation for D and the equation for P. So what do we see? We see a graph that looks a bit like this. So we have effect from price to demand. This is this orange edge here. we have a confounder. This corresponds to the epsilon. And this confounder really comes from the fact that we are resolving the cycle. And I would like to argue that this we need to make use of more often. It would be nice to discuss at some point whether this can also be done more often in physical systems, but this is an offline discussion probably. Okay, and now in this system, you can already guess it, it's called dynamic systems. We observe the system over time. So let me just enroll the full graph. So we observe P and the price and the demand at several time steps. And then the question is again, well, okay, we have this confounder, what shall we do? This assumption of frequency sparsity, what I talked about, this is not possible. So what we are proposing in this project is to go a different route. This is called instrumental variable regression, where you're trying to find a random variable. In this case, it will be wind, that influences the price and therefore also the demand, but it does not influence the demand directly. So here's this reasonable, well, if you have a lot of wind, then in Germany, because of the system, how it's built up, actually the whole merit order curve will shift to the right, if you like, because wind enters with a price of 0. So it will certainly have an effect on the price. Now, the assumption whether it has no direct effect on the demand, this one has to be a bit careful about. So you need to condition on a couple of other variables in order to make this correct, because wind, of course, correlates with winter and so on. So one has to be a bit careful. But let's, for simplicity now, assume indeed wind only affects the price directly and not the demand. Okay, and then this is a system that is well studied. So these instrumental variables, how can we exploit them? Just I'll try to be quick now. In short, you see the effect from the wind on the demand. And because of the structure, you know that this dependence must go through the price. So every dependence that you see between wind and demand, this must correspond to this orange edge, because it never travels via this confounding. This is sort of the underlying idea. Okay, and now what is sort of our, what we considered an interesting insight that we studied is that you can now build up a lot of different instrumental variable regression estimators. So what people have tried in the past, and we believe that this is not exactly the right thing to do, is they just use an instrument, W, the price as a covariate, and a D as a response. And if you neglect the time dependence here, then this is just the wrong thing to do. So what you will get is you could just get an estimate that is biased. So this is not the right answer. So this is a mathematical description that I'm not asking you to understand, but this is a description now of saying there is a theory, and if you have a system similar to this, I'm more than happy to discuss it, but there's a theory that tells you exactly sort of what kind of estimators you can now build in order to estimate this orange edge here. And these are very simple. If you understand the notation, they are very simple rules. They're graphical rules, so you can just read it off the graph, and it yields a lot of different estimators. So this, in short, stands for conditional instrumental variable. It just always tells you, okay, one variable you can take as an instrument, one effect you can try to estimate, and then you can condition on something. And this criterion here tells you whether this is a valid estimator or not. And the one that has been used a lot in the past, according to this, according to us, is not the right thing to do if this is the underlying structure. But there are many other estimators that work. Okay, and now what do we do? This is different in regression, right? There's only one canonical estimator. So what do we do? Well, there's a benefit, right? So if we have a lot of different estimators, then what we can actually say, okay, this is great because we try all of them. And if these work, then they should agree. So we went to the real data and saw whether they just checked whether they agree or not. So this is the effect that we see. And these are different estimators. So these are confidence intervals. And according to this theory, the green ones, they should agree, and they don't. So here you see that there are some estimators that really don't overlap with the confidence intervals. And this is where the economists told us, well, we told you from the beginning that your model that you started with was way too simple. So this here really only meant as an example. If this is the model, so if you falsely believe, I go back one slide, that this is the model representing the truth, what is nice about this theory is it tells you that there are many estimators, many of them should work, and if they don't agree, then there's something wrong in your model. So this allowed us to go back to the model. We made it more complex. So ensure there's a price inelastic demand. This is what they said is apparently important to model. So think about hospitals that have to run in any case, no matter how expensive the electricity is. And then there are cross prices of the type of, well, if I didn't produce in my factory yesterday, I have to produce tomorrow. So these are sometimes called cross prices. And if you do this, the graph looks more complicated, not going into details. Again, you can check what kind of estimators work and which do not work. And then what we get is that this estimator, for example, this still seems to be valid. So this is the current best guess of our price elasticity estimate. This is minus 200. So what is the unit here? So this is minus 200 megawatt per increase of €1 megawatt hour. So this is our current best guess for this price elasticity. Okay, so here are a couple of references. I just show them very quickly so that they are in the video, I guess. And I just conclude here with these two showcases again. So we study dynamical models. And in the first showcase, we try to argue that you can use dynamical models to remove hidden confounding by just assuming that the confounding is sparse in the frequency domain and then trying to let the data speak for themselves. And we very quickly only showed this application to disentangling external forcing from internal variability. And then in the second showcase, we discussed how dynamical models can deal with cyclic structures, again, under this idea of trying to resolve cycles as much as possible. And then we looked at this application to price elasticities, namely what happens to electricity demand if you increase the price. Okay, that's all what I wanted to say. And I'm, of course, more than happy to discuss any questions in case there are some.
Yeah, thanks a lot, Jonas. Very interesting and inspiring talk. Very useful results, even for practice, as we see with this electricity domain. Yeah, are there any questions from the audience? Please go ahead. If not, at the moment, I probably can start with one. It might be the wrong one, because I probably didn't understand everything in the beginning with this frequency domain aspect. So is sparsity the only relevant aspect, or is it probably even difficult if the frequencies of this confounder is somehow not uniformly distributed over the frequencies, but somehow overlaps with important frequencies of the true signal? Does this?
No, that's a very relevant question. So I mean, from now it seems like you understood it. One can make this precise in the theory. So if you are sort of sparse in the frequency, then you are safe to go, right? So if the confounder is sparse in the frequency domain, then nothing bad can happen. So now what happens is I try to briefly mention this, that the X must be active over like many frequencies, because if this is also sparse, then you cannot apply this method. But it's indeed correct that the overlap matters here, but it could very well be that you are overlapping with the frequencies where the confounder is overlapping with the frequencies where X is active. This is no problem. As long as this is it's sparse, it cannot, if you like, it cannot overlap too much.
Yeah.
And so the question is how precise you want to make the theory. So we came up with this couple of assumptions that for the theory, right, that pop out, that make a lot of sense. But then, of course, you could study this a bit in more depth. I think if one were interested, I would probably say that maybe there's an application in mind that this may be even more interesting if there's an application where we are seeing, okay, this could be an edge case, is this actually applicable or not? And then one could look a bit more into, okay, what kind of processes are we dealing with? So the results that we apply, they're working for all sorts of processes, like almost no assumptions on the stochastic process itself. And then, of course, in reality, things are more regular, so it should work even better. That's my intuition.
Thank you. Yeah, we have already some questions from the audience. So Duarte Silva asked, have you ever used conformal prediction instead of prediction using confidence intervals?
Yeah, of course. This is also studied here at ETH. Personally, I think there's still a lot of room for improvement, and I think one has to, let me just think a bit. So my short answer is not in this context, but it should be done. So there's my short answer. But let me just think that there's, of course, in conformal prediction, we get these guarantees, right, that they are marginal. And let me just think whether this is good enough in all of our cases here, because we might. And so, okay, and some of these they are actually. So it's okay. The thing with conformal predictions, of course, we don't usually get guarantees. I mean, there are new versions, but the classical version, you don't get guarantees that are conditional in the sense that if you observe a new X, we are trying to find what is the output of Y. This you usually don't get for. You only get this marginally. So if you say, okay, for if I average now over the axis, what is the guarantee? But I think here this could be indeed interesting to try out. Yeah, we haven't done it. I think it's a good suggestion. Let me know if you find out something useful.
Okay, next question is from Alessandro Antonucci. Very nice topic. I didn't get very well what you said about how to cope with cycles with systems of differential equations. So probably if you can comment on
yes. Okay, so this is also a very good question. So I was, of course, also very brief there. So again, what I'm trying. So this is my view on things, having worked with a couple of real-world applications. My view is try to not use a causal model including cycles without using the notion of time or any other idea that makes it simpler. So if you these models exist, so X is causing Y and Y is causing X, they're just very delicate, and you can already imagine, right, there's a lot of both theoretical questions that come with it. So for example, what kind of distribution does this induce? What happens if I intervene on X? What happens then to Y? Is the system stable or not? Can it explode or not? So there are many theoretical questions that come with it. And my impression is that also on the estimation part, these are very delicate. So if you're saying, I'm now observing data from it, and I'm trying to learn the causal models, I'm trying to find what are the causal structures underlying the data, then this is extremely hard. So the 2 ways out I proposed, or like 3 even, is the first one is just a discrete time, and then the second one was these differential equations. And that is really just saying that these are very simple differential equations that I wrote down. They were linear in their parameters, so very simple. But you're saying the rate of change of a variable depends, let's say the rate of change of variable A depends on the concentration of B, and the rate of change of variable B depends on the concentration of A. If you have a model like this, then there's also, so to say, a cycle, because if I change B, then something in A changes, and if I change A, then something in B changes, but it's much more resolved in time, because now these systems you can actually study very easily, and you can also try to learn. These are systems that naturally arise in mass action kinetics, for example, where you have chemical reactions or chemical reaction networks, and there the reaction happens with a rate that is proportional to the concentration of the reactants. And this is something that, for example, we studied, many others as well, of course, but where the cycle doesn't matter as much anymore. I hope this made it slightly clearer. Otherwise, please reach out.
Yeah, next one is from Michelle Spicer. Thank you for this very interesting talk. Is the sparse infrequency approach limited to additive confounding?
Yeah, that's also a good question. So there's indeed something that cannot be sort of removed extremely easily. We are trying to work on extensions to this, but this is a relevant question. Yeah. So the way I presented it right now, the answer is yes, but we think it can be weakened quite a lot. And there's also maybe one aspect where this becomes directly apparent. So what I presented is saying the confounder is sparse in the frequency domain, but of course you can imagine that what really matters is the effect of the confounder on the response. So even if your confounder is sort of fully expressed in all frequencies, but there's maybe there's a low pass filter in between or something. So the effect of the confounder is actually sparse in the response. Then this is all what matters. And with a similar reasoning, we hope that we can relax this additivity constraint. But again, any insight we also, of course, welcome. And in particular there, if there are some applications that one could study where we know that additivity is probably a bad assumption, then of course this for us always gives a nice starting point for this studying these questions, because it can help us to say, okay, if we don't have additivity, what else could be an interesting assumption to study.
Okay, next question is from Maha Shadadi from my group. She asked how this work relates to spectral decomposition proposed by Gewege 82. For example, subtracting fx linked to y from fy linked to x.
Yeah, I think I would need to get a bit more background to this question. I'm more than happy to discuss maybe offline, but I'm not sure.
I think we can establish the link afterwards.
Yeah, would be great. Yeah.
So Jaden Harrison is asking, can you provide an example of two real-world systems processes where the assumption that the confounder were sparse in the frequency domain turned out to be incorrect?
Yeah, this is of course okay. So there are two maybe two quick answers to this. One is, I mean, it is an assumption and it does not need to hold, right? So I mean, if you think about seasonal cycles, this is just, I mentioned this because they are, I wouldn't say it's sparse in the frequency domain, but of course, if you know it's a seasonal cycle, we can just remove it by hand. But of course, if you have complicated stochastic processes that you don't observe, then there's no reason they should be sparse in the frequency domain. So think about an interesting example that we started thinking about is soil moisture, for example. So it depends now a bit on, of course, what kind of soil moisture. But if this is something that you cannot observe, but you know this should be the confounder, but it's hard to observe remotely, let's say, then the question is, okay, in which areas is this, for example, also only low frequency, or where can it be high frequencies as well? And then it depends on the application. So I think, but if it's just, the confounder is just another stochastic process, doesn't have to be sparse, I would say. The second question to this is, the question is whether we can try to find this out from data. And this we haven't fully exploited or explored either. But we believe that there could be done something, because if you look at if you think about this right-hand side regression plot, in a way we realize whether there's a very good regression model if you just throw away 10% of the data. So this may be an indication that we can just remove 10% of the data and get a good regression. But this is, again, it's a bit speculative, so we haven't done any analysis of this. But it's an interesting question whether one could, in principle, even try to detect these cases. And then, because then you could say, okay, I don't see a sparse confounder, could be anything, so I'm not even claiming anything.
Okay, so I don't see any new questions. Let's see, wait. Well, then I have probably one that relates to this interval selection that you have to do for the Fourier transform. So I guess that things change if the signal is non-stationary. Or can this be applied for any kind of signal to do this?
So the assumptions are really very weak. So, I mean, so what we are, but of course, I mean, okay, so we just have not written it down entirely. If we look at so we are looking at an infill asymptotics, if you like, right? So we fix the interval 0t, and then you just look at infill asymptotics. Now the alternative is that you observe this over time, right? But then you get sort of lower and lower frequencies, whereas what we get is we get higher and higher frequencies, if you like, right? But if you say that your sampling is always like at a certain 1 second, let's say, or 1 minute or 1 day or whatever, and then you just observe it into the future, it's very much similar. You just get the other types of frequencies, right? But it's yeah, I shouldn't say anything before we have not written it down, maybe, but I would assume that also then it's probably possible under very weak assumptions. But as was rightly pointed out, right, the additivity so far you also need. But do you have any processes in mind?
Well, I think
because right now we don't need the stationarity, doesn't matter.
If there are anomalies happen and confounder just comes in, that is probably not there or even just weak in the time series before this anomaly happens. So how would you deal with such a situation? So there's a sudden change.
I think this should be actually fine.
Okay.
I would expect. Maybe I'm missing, but because so you are saying the confounder could be something like a volcano eruption, or?
Yeah, I'm also not on.
Yeah, okay. But so my short answer, but we would need to study this. But my intuition is there wouldn't be any problem with this.
Because in our cases, when we try to do some kind of detecting causal relationships and considering confounding, there was always this problem to figure out the right interval to do the study on. But might be different in your case. I didn't understood everything correct. Yeah, okay. So there are no more questions. But the first example, it's very inspiring for my own classes to show this myopic case. So what is the 8% case? Was it just the number that you?
No, it's just a number that was certainly
there's no.
So
there might be the causal graph that goes from the parents to light, but also light influences myopic, so that you have not a cycle graph. Yeah, but yeah.
No, that is correct. So the study became famous because there's also a bit of discussion in the literature, because at first there was this correlation shown, and then it's also a good example, I think, of slightly imprecise language where they didn't use the word causal, but said that because it's a strong effect, and then you use different words, it's just not the word causal, but that suggests it's a causal link. And then there was this follow-up study that actually found this explanation for the parents, so that actually the parents influence the parents' eyesight influence the eyesight of the children and the lighting conditions for the children. And if I remember correctly, but I would need to study as well, is that they also found the conditional independence, because then there's really no causal link left. So this is
that's true. That was my question. There's really a conditional independence.
Yeah, this is
an additional enforcing factor that comes from the light itself. Yeah. Okay.
It could be, but I think it was at least not apparent in the data.
Okay,
yeah.
Good.
And then just the question, of course, is always that in real life, sometimes you can come up with these ideas, what could it be, right? And this is what they did. So they looked for sort of variables explaining this, and they found the parents, but in many cases, we cannot even think about the random variable, right? And then we cannot measure it either. So this is why I think the more we have, at least to check these hidden confounding assumptions, the better. And in the last, just maybe as a last sentence, so because this is such a hard problem, and we cannot use something like holding out data, we need ideas like the one presented in the second part of the talk, but many others have other ideas as well that are useful. But we need to have ideas to check whether our assumptions make sense. So having, for example, access to many different estimators that all should give the right answer, I think is very valuable, because it gives us the idea of saying, okay, if they don't agree, then we know something is wrong. And this, I think, in causal inference is more important even than in other fields of AI, because we cannot just say we hold out 10% of the data, and if you predict well on these 10%, no matter what you did, sort of the method speaks for you. But because we are trying to predict what happens on an intervention, we need to have these sanity checks.
Okay, so we are approaching the end of our webinar today. I'd like to thank Jonas again for this brilliant presentation and this insightful discussion. Also, thanks to the audience for the questions, and this closes the session. Thank you.
Day's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.